Yes, of course. Ask a question. Yes. For degree 4, 5, 6, 7, 8, 9, as high as you like. And by the way, I'm just saying, it's possible that you have to use it for higher order polynomials at some point in the exam and the homework assignments, the TA sessions. I'm not saying it's going to happen, but it's possible. Okay, so hello everyone. Let's start today's session. We finished chapter 3 and then start chapter 4. Oh, I didn't put it. Oh, all right. I'm very sorry. Yeah, I have so many classes. Sometimes I forget to put one. So yes, there is, of course. So if it's not on the website, I'll add it just because it's useful to have it before tomorrow. So yeah, as soon as I can. Okay. So now we're just going to see a few more examples of equilibria in economics that you may encounter. So there's a way to make it tedious and long and boring. So which I did last time, and I thought it was unnecessary. So I'm just going to make it more. Yeah, I think it's pretty easy for you to see what's going on, anyways, with just an example. All right, so let's just have 2 markets, but you can have as many markets as possible. So why do we call it multi-market partial equilibrium model? Because so if we have a single market, of course, it's partial equilibrium. So why do we still say that if we add just another market, it's still partial equilibrium? Why can it not be a total general equilibrium? So for a model to have a general equilibrium solution, or for a model to be a general equilibrium model, what you have is to have a description of the whole resources available to all market participants, and have to describe everything that people can exchange on every market. So here we're not going to have this. We're just going to see that it's still possible to model the interaction of 2 markets, but without describing the whole economy. So how do we show this? Well, we have well, you just described. So, the demand and supply on all markets, or both markets, I would say. As functions of all prices. So for instance, labor market demand, labor market, market demand equations. So what you would have if you have a single market would be something like QD equals, so let's use Latin letters for this, A plus AP, for instance, A0 plus A1P. And you would have a market supply. So well, we would start with one, and we would have something that looks pretty similar. So QS of, and now let's use Greek letters. Alpha 0 plus alpha 1 is alpha 1P. So here, this is the price on the single market I'm having there. And what if I have a second market? So what I could have is that this is just the first market, and this is just the price. I'm just going to see P1. It's the price, the market price for the first market. And I could have a second market, QD2. And of course, so A1 would be probably a negative, since we probably have ordinary goods. And then I would have a second market. So let's, and then let's just say, oh, in my example, I used B here. Right. Sorry about that. And then, yeah, alpha for the second market. Anyways, it doesn't change anything. And then this would be P2 for the second price. Then for this, I would have, oh, okay, see what's going on. All right. So the supply for the second market, and then I'm going to use Greek letters. Oh yeah, and this is, yeah, beta 1. Yeah, I really want to use the same letters as before, because otherwise I can, oh yeah, and I'm going to write this beta to P2. So then I would have two markets, but you see that there is absolutely no interaction between the two of them, because here the quantity demanded just depends on the own price, and the quantity supplied in that market just depend on the price of that market. And second, same thing for the second market. So the demand for the second market just depends on P2. So what can I do for this? Well, I can, because what I would like maybe is to express the fact that one product is maybe a substitute or a complement of the other product. So I would need to have that the quantity demanded on the first market be both a function of its own price and also a function of P2. So how I would write this? Well, I just add a second coefficient there, A2. And then same thing could happen for, so I would have, yes, so that's why I wanted to write alpha 1 like this. And then same thing could happen for the supply. And here. So both, yeah. So in this way, all market demands and supply may be affected by all prices. Now I need some equilibrium conditions. So what equilibrium conditions do I need? Yes, and how many do I have? Yeah, 2 equilibrium conditions. Since we have 2 markets. Equilibrium. So I need quantity demanded on the market, the first market equals the quantity supplied on the first market. And the same thing for the second market. So that's it. How many unknowns? How many unknown variables do I have to solve? A bit more than 2. What do I not know? Yes, 6. So I have the 4 so quantities. So QD1, QD1, QD2, QS1, QS2. And then I have the 2 prices, P1 and P2. How many equations? So that's an easy question, 6, of course. So I would say 4 behavior conditions or rationality conditions, how you want to call them. Which describe either profit maximization by firms, which is what's the best quantity they can supply given the prices, or the rationality of consumers who just try and do their best to maximize their utility. So this is the description of their behavior. And I have, of course, 2 market equilibrium, or sometimes you call market clearing conditions. So with this, I should be good to go. Do you think I can always find a solution or not? Or how many, so the question more is how many solutions could I have for this system of equations. So here, you don't have to know it in advance. I haven't told you, but if you use your intuition, how many do you think it's possible that I have? Yeah, 4. Yeah, no, 4, I would say, I think is impossible. Yeah. Yeah, okay, take another guess. 4 would mean, so 4 would mean that, yeah, 2, no, doesn't work either. Look at, I have, yes, okay, a lot is good. Infinitely many is good. So look at what I have here. I have a linear system of equations. So a linear system of equations. So if I had quadratic equations, then possibly 2, right? 2 might be good. But here everything is linear. So if it's linear, there's maybe one thing that's describing something that looks like a straight line and the other that looks like a straight line as well. Yeah, don't be sad. It's everybody's learning here. All right, so it's a linear system of equations. So typically you have 3 possibilities. One solution. So one set of quantities and prices which satisfy all the constraints. No solution, or an infinity of solutions. So those who said a lot is good. So if it was something that was quadratic or cubic, for instance, then yeah, you can add as much possibility as you want if you go to higher orders. But yeah, for linear systems, that's typically what we're going to have. And you're going to see that so it's the science and the mathematics of linear system of equations is immense. It's just, it's been, so the first supercomputers that were ever built were in the 50s. First thing they were trying to do is solve system of linear equations. So, or yeah, many different sets of mathematical problems, but big chunk was that. So solving this sort of thing is super useful and maybe quite difficult, because if you have like not 6 equations, but 100,000, 10,000, so you can imagine the number of how many numbers you have in this. So if you don't have a nice way of solving it, then it can be very difficult. So that's a big part of the research in applied mathematics and computer science nowadays. But yeah, it's don't worry. Now we're going to just have simple set of equations. So let's look at how we would solve it. So I'm pretty sure you guys have. Just before this, maybe I yeah, a word on the supply curve. So I have written them this way. So it means that the quantity supply by a firm is function of the price of its own market and the function of the other market, and same for the second one. So from an economics point of view. So does that make sense, or could I make simplifying assumptions here? So here we're getting out of the realm of pure mathematics and thinking about what you learn in microeconomics, or just use your intuitions. So this is how much firms on, say, market 2 are going to supply, and that's a function of the price on market 2 and the price of market 1. So think specifically about what sort of numbers you could have for, well, first of all, think what's the sign of beta 2 here? What's the sign? Is it positive, negative? Yes, it's positive. It's a supply curve. So if the price, sales price go up, then I want to sell more. Good, I want to produce more. But what about beta 1? If I'm producing cars, so if the price of chicken go up, imagine this is the price of chicken, this is the market for chicken. So how much is that going to affect my willingness to produce more cars? Yes, exactly. So it's perfectly possible here to have interaction between the two markets. Because as a consumer, I may think, oh, I should, maybe it's chicken and beef, for instance. So yeah, if the price of chicken goes up, I consume less. So A1 is probably negative. And then beef, yeah, maybe if the price of beef go up, then I consume more. So A2 here would be positive. But as a supplier of chicken, do I care about the price of beef for my production? No, I don't care at all. What I can care, yeah. What this could mean though is something like, say for instance, there is something that's happening in okay, if there is okay, it could be in this particular way. So imagine that something is happening on the chicken market, which also affects the supply of beef in some ways, like there's a big strike of farmers or something. Yeah. Yes. So in principle, maybe you could make up a story, but in general, what we would say is so firms only care about their production costs and the sales price. Yeah, so no, in a way, no, that what I was saying is not necessarily true, but because if it's something that affects farmers, then that would affect beta 0 and B0, regardless of the price of the other market. Yeah, so it's really, really true. So yeah. So in general, we would observe that. So that would be B2 equals beta 1 equals 0. So this would be like this. So we would have a simpler setup, right? How do we solve it? Well, we can let's apply our equilibrium conditions. So yeah, I'm just going to substitute it. So QD1 is this, and QS1 is this. and QD2 is this. And QS2 would be sticky. And then, of course, I can put everything on one side, and then I have two equations, but only two unknowns. So then I can just solve for P1 or for P2. Doing this isn't all that interesting, so I'm just not going to go further. You can guess what's coming. So instead, we're just going to have some small examples. So example. And now take out your pencils and your paper. Because you're going to solve it on your own. I'm going to give you some time to think about it. Equals 4 minus 3P1 plus P2 and QD2 equals 12 plus 2 minus 2P2. So then market demands. Yeah, market demand equation. All right, so just before you start or while you're doing it, so you can answer me some. You can answer some questions. So here, what type of goods good is good one? So here many answers can be possible. So on its own, on itself, or in terms of good two. Then I'm going to ask the same for good two. This is purely economics, especially microeconomics. Don't remember. Did some people were some people in my class last semester or not? Well, don't have to answer, but if you were, I'm disappointed. It means you haven't learned a lot. Okay, I'm going to give you some answers, possible answers, and you choose what is true. Normal, ordinary, inferior, given, substitute of good two, complement of good two. Is it a normal good? You're guessing yes. We can't say for sure. We can say for sure because normal good has to do with income. So yeah, no, they're not independent. See, market one depends on market two, and because there's P1 and P2 here. So normal good has to do with income elasticity. So here, this is all I see is price. Is it ordinary? No, it's not given. Oh God. Okay, so it's good that we. So let me. Yeah. Ordinary good. Price. Because as P1 increases, yes, okay, good, exactly. Demand is negative. So yes, we have -3 here. All right, so it's an ordinary good. And then, so normal has to do with income. Inferior has to do with income. Given would be if this -3 was positive, but that's not the case. Now, is it a substitute of good 2 or a complement of good 2? Substitute, yes, good. So cross price is, oops, positive. So what this means is if the good 2 becomes more expensive, I want to consume more of good 1. So probably what I'm trying to do is make up for the fact that I can use less of this good. So I'm finding a substitute, and a good 1 is a substitute. All right. What type of good is good 2 then? Is it an ordinary good or a given good? So it's ordinary good. So because the price elasticity is -2 here. And it's also a substitute of good 1 because the cross price elasticity of demand is positive. Oops, did I miss something? Yeah, I think I didn't write it properly. 12 plus 2P1. All right. So that makes more sense. Okay, so please solve this. So I'm just going to wait 5-10 minutes until somebody has an answer. Of course, I'm not giving you the market equilibrium conditions, but I assume you know them. Please find the market equilibrium. That's a good right. And 2 unknowns. There's no. Okay, we have an answer. Well, I don't remember what this is, so let's try and find it. So this is equal to P1, and this is equal to 2P2. So let's put everything on, yeah, let's put all the P1s on one side. See what we get. So here I get 4P1, and then I get minus 2P1 minus 4P2. So let's what we could do is multiply this by minus 2. So I would get 4P1 equal minus 24 minus plus 8. So then I can use this equation equals to this equation. So this equals to this. So 7P2 equals to 28. So P2 equals 4. I think many people got different things. So this is a risk. This is a risk for me to give problems that take a few operations at the exam, because for sure people make computation mistakes all the time, make mistakes all the time too. So that's so yeah, I'm totally aware of it. So that's P2 equals 4. So I can put this there. And then P1 equals, so plus 4. So P1 equals 8 divided by 4. So 2. And then substitute P1 P2. in previous equation. All right, so for instance, I can so this is so it's 2. This equals 2 times 4, 8. Why does 4p1 equals 4 plus p2? Oh, here from this, I copied this here. 4 minus 3p1 plus p2 equals to p1 here. So then minus 3 on both sides, I get 4p1 equals 4 plus p2. Right? So that's always what we're trying to do. We're trying to use our equations and substitute variables to get rid of them. And so it's the same thing we would do with 2 equations to unknown system, but we just start with more. And here we apply our equilibrium condition for 2 equations, and then, yeah. So in this case, yeah, we find this, and this is of course equal to the demand as well. So here we found okay, maybe I made a mistake. You're referring to 4p1 minus equals minus I'm going to say what I did here. Here I took this and I multiplied it by minus 2. So times minus 2, I get 4. Times minus 2, I get minus 24. And times minus 2, I get plus 8. Does that make sense? And then with this, I get 4p1 and 4p1. Yeah. So of course, there's no one way to do it. You do it the way you like. Maybe there's some other variable you'd like to get rid of. So here I got rid of the p1 this way, but you can get rid of p2. So we found one solution, one unique. So which is so this equals to 2, 8, 2, 8, and 2, 4. All right. So that's the solution we found. So what does it mean to find infinite number of solutions? Do I have a good example of this? If you can assign parentheses to a given variable, parameters. Sorry, if you can assign parameters to a given variable, what do you mean by this? So the parameters are links between the different variables. Yeah, so what you're saying is, would you like like to have me solved for this general form? I can do that. It's just it's slow and painstaking. Because yeah, you have all these variables lying around, but yeah, you get a solution. Is that what you're saying, or? Okay, yes. So that's where I was going with this. Exactly. I think what you're saying is, what if I have no solution or many solutions? Yeah. So curious. So imagine that I just substituted. Imagine I'm at this stage there. I just substituted P1 and P2. I only have prices, and then I have when can things be problematic? So imagine the following system. I get so 4 plus 2P1 plus P2 equals 0. And then I get 4 plus 4P1 plus 2P2 equals 0. Then what solution is what's the solution for P1 and P2? Infinitely many. I can't do it. Yes, that's the right answer. I can't do it. Sorry. Yes. So no, not infinitely. You have no solution whatsoever here. Because let's divide the second one by 2. So we get 2 plus 2P1 plus P2 equals 0. So here we're saying we want something where 2P1 plus P2 equals 4, and also something where 2P1 plus P2 equals 2. So I can just use the first one and substitute with the second one. So what I'm looking essentially is 4 equals 2. Is that possible? No, it's not. It's not that math is broken. It's just that I have given you a system of equation in which you cannot find a solution P1, P2 for P1 and P2 such that both equations are simultaneously equal. So so in this case, the system has no solution. Now imagine the following. So let's say I have here something that looks like this, but that's 8, and even like, yeah, 10 but equals to 2. So how many solutions do I have for this one? Oh, Naftesh Singh Soi, you're asking, why do I have no solution? Yeah, okay. Yeah. Because what you can do is substitute 2p1 plus p2 equal 2p1 plus p2, and you find that 4 equals 2. So that's, yeah. How about this? How many solutions do I have? Yes, in this case, let's subtract 2 and divide by 2. Second. So I get -2 on both sides. I get 0 here and 8 here. And then I divide by 2. So I get 4 equals 2p1 plus p2 equals 0. So how many solutions for this system? Where the first one is 4p1 plus 4 plus 2p1 plus p2 equals 0. And the second 4 plus 2p1 plus p2 equals 0. So here we have an infinity of solutions. So what this is we essentially have it looked like we had 2 equations, but we essentially had only one, because they describe the same set of points. So how many solutions are compatible? Well, you can, if I have p1 equals 0, then I can have p2 equals -4. If I want to have p1 equals 1, then I have p2 equals -6, and I have an infinity of solutions. So again, this is the problem. So what was common to these 2 cases? So this case and that case, what was the problem in each one of them? So here we got no solution. Here we got an infinity of solution, but there was one common thread, one common issue. Yes, bingo, parallel lines. Yes, so the problem is the coefficients of P1 and P2. If I express P2 as function of P1 for here and here, or here and here, then I would get that I have the same slope. So if I have different slopes, then since they are straight lines, they have to intersect at some point if there are different slopes, because they're just going to cross at some point. If they have the same slopes, then it means that they are parallel lines. What happens with parallel lines? Well, either they are not the same line and they never cross, so it's this situation here, or in this situation they are parallel but they happen to also have the same intersect. So it means that they are just going to completely overlap. So let's just show this. Yeah, so problem if the equations of two variables describe lines if they have the same slope, then they either never cross, no solution, or are confounded. They are the same line. So they have an infinite amount of solution. All right, so let's go ahead and look at that case, for instance, first of all. So that was, so I have only one. Yes, it's easy to remember that. So 4 plus 2p1 plus p2 equals 0. So let's have this like that, for instance. Yeah, like this is fine. Okay, so P1, so we have, let's see, we have P1 here, and P2 here. So if P1 equals 0, then P2 equals 4. Rather, no, P2 equals minus 4. So this is one point. And if P2 equals 0, then P1 has to equal minus 2. So here. So that's our starting. So let's have this blue. Okay, so -2 and -4. So the second case was confounded line. So let's have a second one. Say red. So this is confounded. And the other one was, it was 2, right? So the other one was 2 plus 2p1 plus p2, if I remember correctly. Yeah, 2 plus 2p1 plus p2. So it means that, so p2 is -2 rather than -4. So I would get, so let's take another, so green, for instance. So I think it should be that way. So let's have something that's parallel. Just check. So if P2 equals 0, then P1 equals -1. 0 minus 1. Yeah, that's all right. So that one is parallel. Parallel and distinct. I'm just going to add a bit more stuff in my graph. So here I have -1. Yeah, not the prettiest, sorry. But, yeah, can guess what's going on. Oh yeah, let me keep the okay. So here this is. So is that clear? So and I could have had added the case where they cross, but that's trivial, right? That's the one we know. So when did we start? At 1:15. So we go until 2:30. Am I mostly good here, or do I still have stuff to tell you? Oh yeah, I have a few things about. All right, I can just describe a bit. Yeah, so general equilibrium. Yeah, so that's it for. But this is the important thing, because knowing whether you have 0 solution, 1 solution, or an infinite number of solutions, this is going to take up a big chunk of our time for the foreseeable lectures. Plus, you have to deal with this for the next homework assignment. General equilibrium, yeah. So such incorporates consumer preferences, and budget constraint. So here we haven't talked about budget here. We're assuming that if you spend less or more, then it somehow maybe comes out of the budget of some other market. Who knows? There's no budget constraint in this model. And I could have also dynamic models, which has economy with growth. So in GDP, population, etc. which is not stable, but may have stable growth, which we call balanced growth. So these are we're not touching now. So this you touch in. All right. This you touch in macro. This you touch more, I would say, in a more advanced macro class. But yeah, we don't deal with that today. And yeah, a few words about summations. So we're going. So the next chapter, I'm going to. So it's all about linear equations, linear models, but in a much more structured way. So here we have just 2 markets, or you could add more markets, 3 markets, 4 markets with as many prices as markets. But so how do we go to 2, 3, 4, 5 equations and as many unknowns? So we need a more systematic approach to all of these things. So I'm really going to introduce this in the next week when we deal with linear algebra. So I'm assuming up to now it's kind of some stuff about especially about finding rational roots was probably new. It was new for me when I started teaching it, but the others, it's something that you may have seen previously. But now linear algebra is going to be quite new, I would say, I would imagine. Yeah, maybe you saw that in cégep or college or end of high school, but yeah, mostly for most people, I think it's so totally different topic that's going to be helpful. So notes and summation. So that's the writer, rather this one. All right, so what's a summation? So x1 plus x2 plus x3 plus x4. So you can write this more easily this way, summation from I equals 1 to 4 of xi. So probably I would assume for a few of you, it's something that you already seen before. You can say yes or you can say no. There's no shame. Yes. All right. Oh, so if you've seen calculus, then this class is must be a breeze for you, I assume. All right, but yeah, so take it as it is. You're going to have a very good grade in the class, so I take it. Yeah, so I'm just going to give you some 3 plus 4 plus 5 plus 6. So that's equal to sum of 3 to 6 of I, right? So here is I'm just having the I substitute for the indice of every. Yeah, calculus is not necessarily easy, but don't worry, we don't see integration here. We just see derivatives. We see a lot of optimization though. But yeah, the hard part is next class, I would say. This is more like laying the groundwork for everything that's to come. Yeah, so again, what am I doing here? I'm saying that I'm introducing this variable I, which starts at 3 and then moves in discrete increments, so 3, 4, 5, 6, so 3 to 6. And summation means I sum them up together, so that's the same thing. All right. So some properties, sum of I equals 1 to n of xi plus, plus another sum, but importantly, that has the same limits, so 1 to n and 1 to n, then this is addition, right? So it means I can combine stuff together. So here it's, yeah, so what I can do is associate these two, get this. So the sum of psi plus yi. Simply, if you have 3, 4, 5, 6, 7, 8, 9, 10, so it's like the sum of I equals, yeah, no, in that case, that won't work because the limits would be different. Other property, sum I equals 1 to n of axi. So if all of the elements here are multiplied by a, then of course it means that each element is multiplied by a. And of course it means that I can put the a in front of it, right? So yeah, that's. Are you in disagreement with this one here? Third line. You're saying, are we dealing with series? Should not be sum xi plus sum yi? Oh yeah. Sorry, yes, you're right. All right, so this is equal to, I can just, since this doesn't change, then it's the same for every term. So I can just put it in front of the parentheses if I put things in parentheses. Some useful polynomials. Yeah, useful for polynomials. So I could say something like this. So what do I get? I get a0, x to the 0, plus a1, x to the 1, plus a2 squared. So it's of course equal to a0 plus a1x. So that's if you want to have a compact way of expressing a polynomial. So you just put all your, but of course the thing is these AIs are specific to each term. But yeah, that's a way to. All right, infinite sums. I don't know if you remember this. So if I have the sum for I equal 1 to infinity of 1/2 to the I. Oops. So this, of course, equals 1/2 plus 1/2 squared. So that's 1/4 plus 1/8 plus that. So this equals what? Yes, equals 1. And if you have, so the value of an infinite sum is the limit of its partial sum. So by partial sum, we mean we add up the first element, then the first and the second, then the first and the second and the third. etc., etc. So here you would say this is equal, this converges to, yeah, so partial sum previous sum. So that would be S equals to 1/2. So that's a series. So that's 1/2 plus 1/4. So that's 3/2. Then 3/2 but plus 1/8, that's 7/8. And you see that this converges. Oh yeah, I'm a bit over time. You give me like 2 minutes, maybe I'll just give you some of my other examples. So it's not, yeah, it's quite, so something that you can have is products. So it's the same idea, but instead of adding up together, you multiply together. So let's just use the first example there. So x1 multiplied by x2 multiplied by x3 multiplied by x4. So that's the same, it's just that you express it this way. So this is useful for, yeah, for many things. Yeah, and a general version of this one, I'll just stop here. So this is 1/2, but I could have r to the I from 0 to infinity. And it's equal to r to the 0 plus r to the 1 plus r to the 2. And this is going to be equal to 1 over 1 minus r. For r smaller than 1. And you can see for yourselves why this is the case. If not, I'll show you next class. Oh, and a small quiz that I can give you before leaving. So I'll put it as usual in the. All right, so I'm done. Sorry for going over time. So if you have questions about the homework assignments, anything, just ask. Oh, and tomorrow you're going to have your first TA session without me. So yeah, we have a TA there. I'm meeting him right in a few minutes. So thanks everyone and have a nice weekend.